So good morning, students. So as I said in class, I'm going to do a video on going through some of the problems. So this is going to be the extra practice for acid-base questions. So I'm going to try to go through the last two as I find those ones to be the most challenging, but also cover the most concepts all in one question. So we're going to go over this one and this one. Okay, I especially want to go over this one because most of the time we look at which one is the strongest acid. However, on this one, we're actually looking at bases. So you have to think about the problem in a different way. Okay, so on this one, we're going to use ARIO. Okay. And as a reminder, ARIO stands for atom, resonance, induction, and orbital. Okay. Now, most of the time when we're looking at ARIO, we're looking for which one's most stable, thus which one will make the strongest acid. And if you think about it, if something is a strong acid, then it's a weak base. And if something's a weak base, then it's a strong acid. Okay, so on this one, instead of looking for the most stable one, we're going to be looking for the least stable one. Because if it's less stable, then it'll be a better base. Okay, so keeping that in mind, let's start thinking about how to look at this one. So first thing we're going to do is we're going to look at atom. Okay, so atom effect, we're going to look at which atom has the negative charge. So on these ones, it's mostly going to be oxygen. However, on here, it's going to be nitrogen. Okay, so this one's the one that's different. Now, what we know about oxygen is to the right of nitrogen on the periodic table. Thus, oxygen is more electronegative. Okay, and because it's more electronegative, it actually holds those electrons better, which will make it a better acid. Thus, it won't be as strong of a base. So this nitrogen is actually a stronger base. Okay, it's a stronger base because once it grabs that hydrogen, it's going to be more stable. Whereas in the oxygens, they can hold that negative charge better. They don't need the hydrogen quite as much. So this one is going to be our strongest base, according to atom effect. Okay, now we look at them again. Okay, so we already looked at atom effect. Now we have to look at resonance. Okay, according to resonance, how do these differ? So this one right here, this one has all those valence electrons, and then they have all these double bonds inside. So what this one can do is it can drop the electrons to make a double bond onto the ring and move those electrons. Okay, so if we draw that resonance structure, it's going to look like this. Oh, yep. Okay, good. So we have that negative charge, we have all the electrons. Okay, so we can see that this molecule does have resonance. Okay, so let's keep that in mind. We have resonance. Resonance helps to stabilize this one. So we have to keep in mind this one's actually going to be more stable because it has resonance. Okay, and then remember for a base, we want it to be less stable. That way it needs that hydrogen more. It's going to be a stronger base. Okay, so this one is very stable. Here, we'll put resonance stabilized. Are stable. Okay, now let's see if any of the other ones have resonance. Okay, so let's look at this one. So this one looks like it has resonance. So let's double check it and make sure that it does. Okay, it has the lone pairs. It's in the same spot as the other one. So we should be able to resonate exactly the same. Okay, and I'm going to draw the resonance hybrid just so that we can see that. Also to save myself a little bit of time. So the resonance hybrid is going to look like dots wherever a double bond could have been. So it should have dots all the way around the ring to represent that double bonds can be in any of those spots. And I'll put the partial negatives on here. So I know there's one there. I know there's one there because I saw it over here. Then if I drew out the rest of them, I should be able to see a negative charge here and a negative charge right here. Okay. So we can see both of those are resonance stabilized. Oops, let's put that in green. Okay. So as we said, the more stabilized it is, the weaker the base it is. Okay. Now let's look at which ones don't have resonance. Okay, so this one here does not have resonance, and this one here doesn't have resonance. Okay, they're not close enough to the ring to be able to resonate into it, so we know that they're not resonance stabilized. So what we do is we instead look at induction. Okay. So for induction, this one has to do with dipoles. So on here we see that we have a chlorine. Chlorine is a very electronegative atom, so it can pull in a partial negative charge through a dipole, and thus pull it from the O negative. So it'll help to stabilize that negative charge by inducting the electrons, okay, making it a little bit less electron density on the O negative, thus helping to stabilize it. So this one, compared to this one, they both do not have resonance. However, one has induction and one does not. So induction helps to stabilize it, thus making it a weaker base. So this one here is going to be number 2. And this one here is going to be number 3. Okay, neither of them, they both have oxygens. So we looked at the atom. They both do not have resonance, so that doesn't help to stabilize them. Next thing, induction. So one has induction, one does not. Okay, so this one's going to be 2 and 3. Now we go back to resonance. So for resonance, I look at, there's a lot of stuff going on, but we're looking at this one and this one. Okay, so they both have the same amount of resonance structures, so that doesn't tell us which one is most stable. However, what we do see that is different is one has induction through the chlorine and one does not. So that means that one is going to be more stable than the other. So this one has induction, it has resonance, it has an oxygen, thus it's going to be more stable than the one without the chlorine. Okay, so remember, if it's more stable, it's not going to be as strong of a base. So this one's going to be the weakest base, and this one's going to be the second weakest base. Okay, so that's how we're going to use REO to be able to understand if a base is weaker or stronger. And again, practice with this a little bit just because it's the opposite of what we usually do. Most of the time we're looking at acids. So this one, we're thinking of it in reverse. Okay, we're thinking about which one is least stable. Whereas in acids, we're looking at which one's most stable. Okay, so now let's look at the next one. So this one is determine which of the hydrogens attached to the following molecules is most acidic. So again, we're looking at, or for this one, we're looking at REO again, but we're looking at acids. So instead of looking for least stable, we're looking for the most stable once we have that negative charge. And on here, what I would suggest is to draw in all the hydrogens. Or at least all the unique ones. Okay, because that way you can see all your options of which hydrogens you can pull off. Okay, because you want to see these two are the same, so I'm going to erase one. You want to see what your options are for negative charges and then try to eliminate them by seeing which ones are most stable, which ones are least stable. And we'll do that using ARIO. But let's draw a couple of our different options. So I'm going to draw a base. I'm going to draw the mechanism once just so I make sure I'm drawing it correctly. A lot of times I forget which charge it has, so I draw it out so that I remember. So if I pull off this hydrogen, I'm going to leave a negative charge on that carbon. So I'm going to redraw that with a negative charge. Oops, there's no carbon there. Okay, and then now I have negative charge here. Okay, so that's how I'm going to draw my conjugate base. Now I'm going to draw a couple different options just so that I can see where my negative charge can go on, depending on which hydrogen I pull. So now let's see, what if I pull this one? I'm going to put the electrons right here. Okay. Now I have this negative charge here. I have this double bond O. I have those. Okay, next option. But if I grab this hydrogen over here, I'm going to put the negative charge on the carbon. Negative charge here. Okay, and then last one. Going to be this one. And I know this is a lot of work, but I highly recommend that you go through all these steps because just so that you don't miss anything. Also at the beginning, you never know which one's going to be the most acidic just by looking at it. So practicing and seeing different options is very important. Because now I have 4 options. Okay. And again, we're going to use ARIO to be able to see which of these conjugate bases are going to be the most stable. Okay, so the first one is atom. And so all of these are on carbon. So as of right now, there is no difference in atom between any of these. Okay. The second step is resonance. Okay, so we're going to see if any of these have resonance. So just in case, sometimes it might be better if you draw in your hydrogens just to make sure you don't resonate anywhere that you shouldn't. So for example, here, sometimes I might think about resonating onto that carbon to make a double bond, but I can't because those hydrogens are there. So I would have broken the octet rule. So that one doesn't have any resonance. This one here is on a carbon. But as you can see here, this one is a quaternary carbon. So it has 4 carbons around it. So that one's not going to have any resonance. It doesn't have any pi bonds to attach to, so no resonance for that one. Okay, this one right here. Sometimes we think it can resonate onto here and push these up. Okay. And the thing is, this looks like a fine resonance structure. It looks a little weird, but according to octet rule, it should be okay. However, I'm going to tell you right now, this one does not work. Okay, the reason why is because of, if you remember hybridization, oops, if you remember hybridization and shapes, right here, this is going to be an sp carbon. Okay, and if you remember correctly, an sp carbon has the shape of linear. So because of that, this is in a ring and there's no way it can be linear. So this carbon is not going to want that shape and it's actually going to reject this. So we cannot have that resonance structure because of shape. Okay, so that one's not an option. So we don't have any resonance on that one. Now let's check the last one. I'm going to move this a little bit just so I can get to those lone pairs. Okay, and this one, it can resonate right here. Move this over here, move this onto the oxygen. Okay, I'm going to give myself a little more room. I'm going to move these over here. Okay, so I have the resonance structure for this one. gonna look like this. O negative, and then like this. Okay, just to make sure, I'm gonna put these in brackets so we can tell that those go together. So as we can see, one of the hydrogens, if we pull it off, has resonance. Okay, so this one is going to be the most acidic hydrogen, which correlates with this one right here. Okay, most acidic. Okay, it's a bit of work, but I highly recommend look at all of them. Make sure that you know exactly which one's going to be the most acidic. Okay, go through all of the different options and see which one is going to be best. Okay, now let's try this for part B. Okay. Again, we're going to use Ario. But let's draw in those hydrogens and see what options I have. H, H, I have H's over here. Okay, and I'm gonna erase any that are on the same carbon. So these two, this one has 3 on it. So it's 2. Oops, I went, yep. Okay, good. And then I'm gonna erase one of these ones. I'm gonna erase this one. And then I'm gonna erase 2 of these ones, just so I have one hard, um, the unique hydrogens. Each of those are on the same carbon, so they would have been the same options. Okay. Now, again, I can draw all the different options and then see which one has can follow Aria. Okay, so first one I'm going to draw is I'm going to draw this one. Okay, if a base takes that one, it'll be HO with a negative charge here, PR, and then don't forget these carbons. Okay, so we'll put that as option 1. Okay, I'll put this one as option 2. So I'll draw the same thing, but I'll draw the cation for when my base took away that hydrogen. Okay, option 3. And the negative charge goes here. Actually, this one will be exactly, well, no, it won't. It's different. So let's try that one too. Okay, this will be option 4. Oops, I hit the wrong button. There we go. That's what I wanted. Okay, negative charge here. Okay, option 5. Negative charge right here. Okay, and there's actually a 6th one that we forgot, which is actually one of the most important ones. So it's actually this one right here, 6. So make sure that you don't miss any of the hydrogens. Okay, now if we look at Ario, oh, Ario is always the first one we're going to look at. This one's on a carbon, 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 and this one's on carbon as well. However, this one is on oxygen. So if we look at this, Ario tells us that this one is going to be our most stable carbocation. Uh, sorry, going to be our most stable conjugate base. There we go. Okay, and if it's the most stable conjugate base, that means it's the most acidic. So this one here, most acidic. Okay, so that's going to be going through those questions for acid base. Please let me know if you have any questions in class. I'll see you guys later.